we're given a graph of g of x. We want to do a vertical compression of 1/3 and then a translation of 2 units up. So if we were looking at the points that we have, and I labeled the points that we have off to the side here, can you see that we have -5, 3 as this first point, -2, -3 as a second point, 1, 0 as the third point, and 4, 6 as the third point, as the fourth point. And since we are supposed to do a vertical compression and then a vertical translation, when we're showing our work this way, we're going to need to do 2 sets of arrows. Our first set of arrows is all of our stretches and compressions, and we only have the one stretch and compression. We have to multiply our y value by 1/3. And we only have one translation. We need to go to up. We need to do the 1/3 first. That's just going to affect the y value, so all of my x values are going to stay the same. And multiplying by 1/3 will change my y values. Then after I get that new point, now I have to shift things 2 up. Again, my x values are not going to change. Add 2 to each of my y values. And we get our final points. Again, the math is so easy that you're going to make little errors just because you don't pay attention to it. Adding 2 is like super easy. You're going to make mistakes adding 2. So when we get our final graph, so I'm going to now label -5, 3, well that's right there. That point didn't change. -2, 1, 1, 2, and 4, 4, and connect the dots. We have to ask ourselves, does this appear to be right? A vertical compression means that it's been squished towards the x-axis. Our graph does look squished. Does it look like it's then been moved up? Yes. So it appears to be correct. It says label the image, okay? Maybe they mean label the points, so we should label that this is 4, 4, 1, 2, -2, 1, and -5, 3. Labeling the image might also mean that we want to write the equation in terms of the function g. So in addition to labeling it there, I'm going to write the equation in function notation. In other words, in terms of the function g. So how do I do that? Well, I look above my arrows and say I have a vertical compression by 1/3 and a vertical translation 2 up. Both of those things are vertical. They're going to happen outside of the function. Where does the 1/3 show up? That shows up as multiplying in front of the function. And where does the 2 up show up? Outside after the function. So this will be the equation in terms of the function g. Now something happens important with horizontal stretches and translations. So we're also going to do together the textbook example. So we're going to go to example 1. And it's exactly the same as the one off to the side, but this time they say there's a horizontal compression by half, then a translation 3 units to the left. So we start off exactly the same as before. I'm going to label the points that are on there, -4, 3, 0, -2, 2, 5, and 4, 2. Draw two sets of arrows because we have a horizontal compression, so that means x is getting multiplied by half, getting a new point. And then 3 units to the left, so we have to do those separately. Since everything is horizontal, now my y values are not changing. Multiplying x by half. And then when moving 3 to the left, my y values won't change, but my x values will. -5, -3, -2, -1. I plot these points. -5, -3, -3, -2, -2, -5, and -1, -2. Does it appear that we've had a horizontal compression squishing towards the y-axis and then moving it 3 to the left? Yes. So far, everything in this example has been identical to what we did on the one on the side. But the thing that is tricky is now I'm going to get you to write this equation in terms of f of x. So we're going to write the blue equation in terms of f of x. I'm going to provide two possible answers that both appear to be right, but one of them is right and one of them is wrong. So don't write down the equations yet, because we're going to determine which one is correct and which one is wrong. Equation 1 looks like this. Y equals, everything happens inside of the function. So I have x by half, and I remember that that means multiply by 2. And then I need to move things 3 to the left, and 3 to the left, that would show up as +3. Option 1. Option 2, or y equals f, everything is inside the function, to the x, and then move 3 to the left, I go +3. The difference, the first one has an extra set of brackets. With the first one, if I actually distribute that, I get 2x + 6, right? With the second one, I get 2x + 3. Which one looks simpler? Second one. Okay? Which one do you think it is? Second one, because it's simpler. Okay, how many people think it's the first one? Because it's more complicated, and math is complicated, so if they're going to do something, they're going to make it more complicated. Yeah, see some people nodding to that. Okay? Everything inside the function has been more complicated, right? Your 2 is multiplied by half. Your +3 is actually 3 to the left. And it is true that this is the correct one, and this one is incorrect. Again, against what your gut feeling would probably want to say. Yeah, when you distribute it, you get 2x + 6, but it would still be moving it 3 to the left. So at the bottom of this page, everybody is going to write this, because this is going to be something that's hard to remember, so we're going to make a special note. When you have I could write this all out. Are you okay if I write horizontal reflection or horizontal stretch or horizontal compression? Are you okay with those abbreviations? When you have a horizontal reflection, stretch, or compression, and, that's a bad, capital letter and a horizontal translation. You must, capital letters, you must write it in factored form. Yes. Why? Well, if we would we'll take a graph where it's actually a complicated graph where it's easy to see why that happens. Okay? The most complicated graph that we've learned so far is your reciprocal graph. Okay? Or I can write this as f of x equals 1 over x. If I took the graph of this is equivalent to that, right? I can distribute the bottom, it's equivalent to that. When we think about our original graph, right, this is what it looks like. It has an asymptote here. And the reason I chose this graph is because the asymptote is really going to tell us what's happening. If I have it in the non-factored form, which is right here, that would tell me to go 15 to the left. If I have it in the factored form here, it tells me to go 5 to the left. When I move this left and right, can you see my asymptote is going to move? And my asymptote represents the non-permissible value. We can't divide by 0. That's why there's an asymptote there. What would make us divide by 0 here? Negative 5. Which would move it 5 to the left. What would be our non-permissible value here? Still negative 5. Negative 5 is still our non-permissible value in that second one. We still need to move 5 to the left. Okay? Even though we see that plus 15. So when it's in this form here, you would factor out the 3 and write it in this form. The only hint I gave you that would make you realize that that was the right answer is if you go back to the example we did to start off today with the square root. And we look at the equation how they wrote it. Do you see inside they factored out the 2? It wasn't 2x plus 3, it was 2 bracket x plus 3. So there was a little tiny hint for which way it should be. But it was really hidden. So we have this special note. Okay? One year, I had a student who was like, I'm going to forget these things. Everything that you think is important, Mr. Jerry, let me know. And they started setting up a reminder thing on their phone. So this was their first reminder. At 10 o'clock every night, their phone buzzed. And this came up. Remember, when you have a horizontal stretch, compression, or reflection with a horizontal translation, you have to write it in factored form. And every night at 10, they were reminded of that. And then they found out something else important. I mean, if you did that with all of your classes, you would probably spend from 6 till 11 with every 3 minutes getting a buzz of something else on your phone. But it might be helpful. It was helpful for that student. Certain things they did not forget at the end of the year because they were reminded of it every day on their phone. Might be an idea. Oh, questions for number 1? Questions for number 1 are 4, 5, and 6.